Hi there. In this video we're going to talk about spherical geometry. We're going to introduce the sphere, which is our first example of a non-Euclidean geometry. Then we're going to talk about how Euclid's fifth postulate relates to the sphere. Then we'll get into the orthogonal group, the role of poles and polars, and we'll finish off with Gerards Theorem. Let's get started. So the sphere has a standard model. We're going to use one particular model, but all spheres in Euclidean space will work. But we're going to look at the unit sphere. So we're going to look at all of those vectors, v, that have length 1. Alternatively, we're going to look at when x squared plus y squared plus z squared equals out to 1. Now, if we pick a plane pi passing through the origin, then we can define a line on the sphere as the intersection of that plane with the sphere. Right? So we take our sphere and we cut it via a plane. So in this picture, we have the sphere is here. This is S2. And then we have our plane pi. And the intersection of those two objects gives us the line L. Okay, so in spherical geometry, the lines are these sort of generalizations of the equator obtained by intersecting flat planes with the sphere. Okay. Now, I want to look at Euclid's fifth postulate and how it relates to the sphere. So the fifth postulate says that given a line and a point not on that line, there is a unique parallel to the given line passing through the given point. Okay, so this sort of characterizes geometry in the plane, and I want to point out something strange that happens when we look at the sphere. So if we are given a particular line L, right, we focus on this line L here, and we pick a point P, then we get this interesting situation. Every line passing through P intersects L. So there are no parallel lines in spherical geometry. We have that every pair of lines, in fact, intersects in spherical geometry. So what we obtain is that Euclid's fifth postulate does not hold in the sphere, and hence we say that the sphere is a non-Euclidean geometry. Just as a question, something to reflect on, what about the other postulates of Euclidean geometry? Do they hold in the sphere? Now I want to get into the orthogonal group. The orthogonal group is the transformation group of the sphere, and it's defined as all of those 3x3 matrices that preserve the inner product on Euclidean space. So if we take two vectors, u and v, and we take their transformations, tu and tv, we expect to get the same answer before and after transforming via t. We have the following theorem which says if we have a point in the sphere and we transform it according to the orthogonal group, then we wind up with another point in the sphere. So when we rotate the sphere about the origin, or when we reflect across a plane, those are both transformations that live inside the orthogonal group, and so we obtain that those are going to be points in the sphere again. So now we can define spherical geometry together with its transformation group. We start off with the point set of the unit sphere, and we put the 3x3 orthogonal matrices as a transformation group. So that includes both rotations and reflections across planes. Now we're going to talk about some sort of interesting features of spherical geometry that don't quite have analogs in Euclidean geometry. Those are the poles, polars, and perpendiculars. So if we have a line L, then that'll determine for us a plane P, a plane pi, right? And that plane pi has a normal vector. So this is the normal vector of the plane pi. And what we wind up obtaining is we wind up that there are two places where that normal vector will meet the sphere. Right, so these are the poles of the line L. Okay, we take the line L, and it determines for us these 2 points on the sphere, kind of the North Pole and the South Pole with respect to that line L. And alternatively, we can go in the opposite direction, and starting from a point, we can define the line that has that as its pole. Right, so this is going to be called the polar of that point. So given a point, we get a line that is sort of the equator with respect to that point, and that's called the polar. And given a line, we get 2 points that are the poles of that line. Oops. Okay, so notice, given a line, we get 2 poles, and given a pole, we get a line polar to it. Okay, these are interesting relationships, and there's not really an analog of these in Euclidean geometry. Now I want to state one of the most important theorems in spherical geometry that we're going to investigate in class, and this is Gerards Theorem. So Gerards Theorem is remarkable in that it was a question that lots of people wanted the answer to for centuries. You know, ever since people started looking up at the sky and wondering about the orbits of planets, people wanted to be able to calculate areas on the sphere. And after centuries and centuries of work on this, Gerard came up with an answer to this. So this is a very, very beautiful theorem, and what it tells us is the area of a spherical triangle. So given 3 lines through some points A, B, C, we can form angles alpha, beta, and gamma. And notice that this triangle here notice that this triangle has, on the opposite side of the sphere, sort of a twin. There's a twin triangle that lives antipodal to the triangle ABC, and we'll call that triangle A prime, B prime, C prime. So what Gerard's theorem allows us to do is it allows us to calculate the area of the spherical triangle ABC with the following elegant formula. The area of the triangle ABC is the sum of the angles minus pi. So this gives us a very simple and direct way to calculate the area of triangles on spheres, and we're going to investigate this formula in class. Thank you for watching.